We have developed this smart device that is powered by this organic solar panel, and it's a small lithium battery that actually behaves like a supercapacitor in some ways. By the way, this project was presented at CES 2025 at the Nikon booth. It will also be presented in Germany from March 11th to 13 at Embedded World, again at the Nikon booth.
Objects.
In the last video, you asked me a ton of questions and I thank you for the support. Today, I will try to answer some of these because I won't be able to cover all the topics in one video. I'll start with the LPMs themselves, meaning what they are used for, what types of projects can be developed with them, and then over time I'll also address all the other questions, especially regarding certifications for the modules and the products I develop. And not only that, but also regarding the software part, the integration, and so on. So for now, I would just focus on how you use LPM, how it integrates into other projects. And then, in the upcoming videos, we will analyze everything else. Now, to show you, in practice, how LPMs can be used, we have developed 3 very simple demos to explain how they are used, what the advantages are, why you should choose one module rather than another, etc. So, we have 3 smart door sensors. They are different from each other, but they serve the same function, of course, even though there are some small differences. As for the sensors, they are designed to be powered and used in different ways. Let me explain. We have the first version, which is the one on the left. This smart door sensor is based on the ELPM-C6LW, so it's using the ESP32C6. More, apart from the Aura one, so you understand well that if you take a moment, you know the protocol stat on Qi, it supports the ESP32C6R. This version is really multi-protocol, so this module can potentially communicate with most of the hubs you have at home or that you can find on Amazon. And in general, it's useful for both smart home and industrial applications, so indoor and outdoor. Then we have this other one. This version is based on the ELPM-N52-MINI, not shown yet, like the C6LW, now based on Nordic NRF 52840, not ESP32. Supports other protocols, lacks Aura 1 in Mini E. In particular, it works mainly at voltages lower than 3.3, to be more precise at 1.8, which is the minimum operating voltage. The main advantage of this microcontroller, besides its lower operating power compared to the ESP32S3 or the ESP32C6, is its power consumption. It allows you to develop a demo with a coin cell battery, a CR2N32. In this case, first of all, because in Bluetooth transmission or even using Zigbee, you never exceed 7 to 10 mol IAA, and trust me, this makes a difference, especially since it allows us to use batteries like this. Also, this mini version indeed doesn't have the Aura 1 part, but it still has. Power block, then power latch RTC LD, of course also integrated with the Nordic itself. Then we have this latest version which is still based on the N52-MINI, but as you can see there are some differences. First of all, there is an energy harvester here in the center. You may be wondering why. I'll explain why. And finally, on the bottom there is precisely this slot dedicated to a Nikon small lithium battery bara supercapacitor. I'll explain it to you better later. What am I referring to? But in general, this iteration is essentially the energy harvesting version. So through a solar panel, it's possible in essence to power my controller, the LPM, and of course primarily recharge the storage, which is actually a hybrid in particular between a supercapacitor, specifically in this case from Nikon, and a lithium battery. Moreover, only these 2 versions, the C6 version and the N52 energy harvesting version, also have sensors on board. They have temperature, humidity, and air quality sensors. Additionally, the C6 version also has a sensor that I'll explain to you what is it for. But basically, it's a sensor that detects the ambient light. In both cases, we are using Renesas sensors for temperature, humidity, and air quality, which are this one and that one. In the corner, regarding the coin cell version, we only have the reed switch in this case. But in reality, it's also possible to solder a Hall effect sensor. The same goes for the other 2 variants, specifically to test the difference between the red switch and the Hall effect sensor. Before we continue, I absolutely have to thank PCB Way for supporting the development of this project, not just for the LPMs, but for all the projects you've seen on the channel. So if you're looking for a reliable printed circuit board manufacturer for your project, I recommend PCB Way. Also, I want to remind you that PCB Way, in addition to handling the production of printed circuit boards, can manage other types of processing, such as CNC machining or 3D printing and much more. You'll find the link below in the description to place your first order. Thanks again to PCB Way for supporting this project, and now let's get back to the video. Now, as I mentioned a little while ago, the real difference between the three smart door sensor variants is their energy efficiency. And let me mention, the source that powers them in some way, the type of battery. As you can see on the left, the C6LW can be powered easily by either AA or AA batteries. It doesn't matter. In this case, I'm using AA batteries. As for the coin cell version, the socket is designed to hold a CR232. However, you can also use other variants, such as or similar types. It would just be enough to, well, change the socket and enlarge it a bit, PCB Way. And then finally, we have the energy harvesting version, which, as you can see, these are not the common batteries that you're usually used to. Just a moment to look at smart devices, but these are indeed solutions, a bit of a hybrid between supercapacitors and lithium batteries. They're called small lithium batteries, so SLB. Now, before we continue with the video, quickly, showing the advantages of SLBs compared to traditional lithium batteries. First of all, they have a better battery life. Compared to traditional lithium batteries, you can charge them much faster. In 3 minutes, it reaches 80% charge and discharge. You can get 20 times the charge, so I don't know if, for example, the SLB is 100, but you can get an output of 2A discharge for about 3 minutes, then just a moment to see the situation. Then there's the low charging current. This is very useful for energy harvesting, meaning you can charge the SLBs with a really small current, I don't know, for example, from small solar panels. The operating temperatures are also quite interesting as a feature, but particularly the aspect that interests me the most. And especially in some applications that we will develop a bit in the future, the aspect of safety is important. I mean, compared to lithium batteries, they don't catch fire, you can short the terminals without any issues, nothing happens, you won't damage the SLBs. However, it is a very reliable solution that guarantees you of not having problems with the device in the long run. I think it's a really interesting solution for the development of several industrial applications. So how do these smart devices work? So the operating principle is the same for all three. Basically, they are activated through the trigger system using a red switch or Hall effect sensor. So I bring the magnet close and the device turns on. If there are sensors present in the device, it takes those measurements: temperature, humidity, air quality. After that, this data is collected and sent via Bluetooth in this demo in particular. Can other protocols be used as well? Absolutely, yes, like Thread in the case of the N52-MINI or even Zigbee. As for the ELPM-C6LW, you can also use other protocols like Aura, Aura1, or other custom sub-Giga protocols, so it's definitely very interesting for industrial applications. Imagine making smart door sensors for industrial applications, so for a very large facility. These smart door sensors are placed in locations that are a bit more remote compared to in a classic indoor application within an apartment. On the other hand, when it comes to the energy harvesting version, the situation is definitely more interesting. Because in this case, we have a device that recharges itself and generally doesn't need your maintenance for about 10 years, unlike the two previous versions which, yes, are more efficient but are still based on traditional power sources, so batteries AA, or coin cells. This solution, from my point of view, is really interesting, especially for indoor applications because the solar panel, it captures both the light present in an environment, so I don't know, artificial lighting, which can be LED, neon, or any other source, but also, and especially the light coming from, I don't know, from the windows, so external sunlight coming into an environment. The applications regarding this version of energy harvesting is much more interesting. Imagine, I don't know, having to manage sensors in a university campus or even inside a hospital or a factory, and having hundreds or thousands of these nodes, these sensors, these smart devices. So you understand well that if you have a solution that guarantees you continuous, constant daily data ping for 10 years, and this is a very interesting thing. I understand well that many of you might not see the benefit because obviously if we think in terms of 2-3 nodes that I can have at home, that's one thing. But it's another thing to see IoT from the perspective of industrial applications. When you have thousands of nodes, trust me, it changes. 1,000, 2,000 batteries monthly or annually have a cost, but not just for the battery itself, but because you have to pay a person or a team of people who will be responsible for replacing these batteries, and it has a cost that is significantly higher than the battery itself. Now in this video, I won't show you how to program the nodes, simply because there is so much to cover. With this video, I wanted to briefly introduce the topic. I wanted to show you a bit how are LPMs used in the real world? And in particular, I wanted to show you the energy harvesting version now, just to give you a glimpse. How does this energy harvesting version of the smart door sensor essentially work? is very simple. I just bring this magnet close, which as you can see, I've printed briefly in 3D, but inside there's a very simple magnet. I bring it close to the Hall effect sensor. What happens is that it turns on. Now, I'm showing you for a moment. My smartphone turns on for 10 seconds, sends the data via Bluetooth to my smartphone or any other source. It doesn't matter. And it's possible to read temperature, humidity, and also the status of the contact, whether it's open or closed. In general, it's possible to display even more data. I repeat, this is a demo to give you a brief understanding of how it works. I have actually already made other videos, other demos in English with my pronunciation always on the channel. So I invite you to watch those. It doesn't make sense to show you the same thing over and over, also because I have already shown how it's possible to develop a dashboard using the ESP32P4 with the touchscreen display. So I have already shown a lot regarding the possible integration of LPMs, but of course there is also much more to show. In the coming days I will show you briefly how to program the LPMs and also the original official dev kit of the ELPM-S6LW, which from my point of view can be interesting to understand the true potential of the LPMs and the entire OBJEX project.
OBJEX. Please also visit objexlabs.com.